let us begin then. So I have 2 sets of slides. We're going to finish this one completely and then start a new one today. It'll be fun. So containers is a fun little topic. It's just the idea of holding something is a very common thing that you'd like to do in programming. Like to hold on to a bunch of values, like in a vector, in an array. There's so many options. There's so many more than that. We talked about lists briefly. I'll talk about them more today, I believe. Linked lists you read about in your book. That's another way to store a bunch of stuff, right? There are plenty of ways to store things, and some ways are better than others for certain operations. And so let's break that down and talk about it. You will learn much, much more than you could ever hope to want to learn about this in CSCI 41 if you take that. But this is a good sneak peek. All right, so let's first talk about abstract data types, ADTs for short, and then containers in terms of this. Okay, so an ADT is defined to be, abstract data type, defined to be a class of objects whose logical behavior is defined by a set of values and a set of operations. So that kind of sounds like object-oriented programming in a nutshell, right? You have member variables, you have member functions, those are your operations, the values are the member variables, things like that. It's essentially a class in that sense, but I want you to think of it as like a black box. And you can interact with that black box, but you're not really sure how it's implemented, all right? It responds to operations, like you can ask it to do stuff, but you're not sure what the code is underneath. And you also just don't care. As long as it does what you want it to do and you get back what you expect, you're fine, right? So vectors, for example, I have not told you. You have no clue how a vector is implemented right now, right? Unless you read ahead in your book or something. A vector, for all intents and purposes, right now to you is a black box. You can treat it kind of like an array, but you have no clue what's going on. You can tell it to do stuff, and it will do that thing, right? And you assume that it's going to all be coherent. So you can say, hey, push back 2 to an empty vector. And it's a void function, so it's going to be like, sure. It will respond, sure. And then it's the chain of interactions, though, that you know to expect. So vectors, they know how to respond to push back, pop back, at, size. They know how to respond to those messages. That's the idea. So you know that once you push back 2, if that was the first thing that you did, if you say, hey, dot at of 0, it better respond with 2. As long as it plays that game properly, it's a vector, right? You can write anything to be a vector. You can implement your own vector as long as it makes this happen. Okay? There are plenty of ways to do it, but we have no clue what's going on under the hood. That's what an ADT is all about. It's defined in terms of how you interact with it, not its implementation. Operations only. And so that's great. There are a million different ways to implement a vector, and they all have competing options. Okay? And we'll learn about one of the ways, the most common way to implement a vector, in CSCI 41, if you take it with me. All right, container time. So a container is just a type that holds elements. It holds on to a bunch of stuff. That's all. So a vector, it's a container because you can make a vector of ints and put a bunch of ints inside. You can make a vector of strings and put a bunch of strings inside. You can make a vector of vectors and put a bunch of vectors inside a vector. Why not? So vectors are cool. We know and love them. We'll talk about them as well as some of the competing options to vectors as well. Okay. So let's start with vectors. Let's learn about them a little bit more. Let me use some fancier terms. So vectors are containers. A vector is what's called a random access container. Random access container, and it can grow as well. So 8, 6, 7, 5, 3, that could be my vector. A vector is random access because you can go to any index immediately, like 0, 1, 2, 3, 4. If you remember reading about linked lists, you can't get to the middle very easily. You have to follow some pointer chains and stuff. Vectors, though, they're random access, just like arrays. You can get to any index immediately. Like I can ask for index 2 right in the middle and go there immediately and get the value. Okay, no extra work needed. They can also grow in size. So you can push back, and that creates an index 5, put a value there. Okay. If you look up these operations, and again, this will be a huge concept in CSCI 41, if you look up the operations on vectors in the documentation pages, they will have a complexity section. So vector pushback, for example, or just like at, all these things, they are all constant complexity. So like if you say, how fast is it to go to an arbitrary place in the vector with the .at method? Scroll down, it says complexity, constant. That is as fast as possible. It's immediate to get there. The constant is the best possible complexity for an operation, and a lot of the vector operations are constant. Add is constant, size is constant, pushback is constant, believe it or not. Just to add something to the end of a vector, regardless of its size, that happens to be a constant time to do that. It's amazing. But it's a fancy kind of constant, amortized constant time. You'll learn about that at a four-year college. But yeah, vectors are really good for like going somewhere, .at, getting its size very fast, adding to the end, pushback. That's really cool. And so you can move around a vector, right? You can iterate through it if you didn't have any fancy techniques, just by asking for its size, because that will give you like that -1 is the last index you can touch, and then just use .at. You can go everywhere. Okay, so that is vectors. Let me just start a file so that we can just show the differences between all this stuff. Vectors.cvp. So, I don't know, I'll include vector, and I'll make a vector event. That was my vector from the example slide. And, okay, you know how to do all that, that's fine. What next? I'd like to teach you about iterators now. What in the world is an iterator is the first question. So an iterator is a type. It's an abstraction. It's kind of like a black box again over the concept of iteration. So like the idea of going through something, an iterator will do that for you. They're modeled after pointers. So perhaps you have seen these ideas, these functions begin and end. These are iterators. Return an iterator to the beginning of the vector. Return an iterator to the end of the vector. And what is the type of the iterator? It's very weird. It's the type. It lives inside of it. So if you have a vector of ints, an iterator through that vector of ints, like if you ask for that vector.begin, it will give you back a vector of int : iterator. So it's a type that lives within a type, which is weird. But yeah, an iterator abstracts over the idea of iteration, going through something. So v, here's my vector. Eight, 6, 7, 5. If I say something like, I make an iterator, call it it, set that equal to v.begin, essentially, it's kind of like a pointer. v.begin will give back an iterator to the beginning of the vector, and it's essentially pointing to the first index, the 0th index. Right? And the type of v.begin for a vector of ints is going to be vector int : iterator, which is very weird. So that's that one. v.end, you might think it's a pointer, in quotes, pointer, though it's not a real pointer. You might think that it's a pointer to the end of the vector, but no, v.end gives you a pointer, gives you an iterator to one past the end. So you never want to go to the end. You want to stop before you get to end, because that's what end is pointing to. All right. So that's begin. Begin is the start. End is that one. And you can do pointer-like things with iterators. They've overloaded those ideas. So you think of them as pointers, kind of. So like if you say start it, it'll work. Start it right now will give you back 8. Crazy. And if you want to go to the next element, if you'd like the iterator to go through the vector to the next place, you can say it++. Just on a line by itself, and that will advance the iterator to go to the next place, which is really cool. So Think of them like pointers. That means, though, if like I have an iterator, I start at the beginning, I can plus it and star it to get elements, and I stop my iteration once I get to the end. That's another way to iterate through my vector. So let's bring all those together with some fancy types in the process. So if I would like to go through my vector, here's how I can do it. I can say vector, well, first of all, v.begin. What's the type of that? Call it it. What's the type of this? You could totally cheat and say auto, and eventually you will, but right now the full type is vector int : iterator. That is the type of a vector of int iterator. The type is involved. And it functions like a pointer, so I can say cout star it, and that will legitimately, right, begin as the first element. It will give me back the value of that first element. So there's my 8. Cool. I could advance it, it++, and now the iterator will point to the next element in the vector, the 6. And so if I say star it now, it will then go and print the 6 as well. Any questions about that? That's just a new type. It's supposed to simulate iteration. It's called an iterator. Seems a bit complicated though, right? You can use this then. It's another way to iterate through the vector. Here's how you can do it. You can do it in a for loop. For vector int : iterator it equals v.begin. And there's no real concept of less than in an iterator land, so you just say, like, I want to stop once I get to end, like I don't want to continue. So you just say, keep going as long as it is unequal to v.end, and then it++ to advance it every time. And now I could get at every element of the vector with star it. It's going to be advanced each time. So that's a new kind of way to go through a vector. It's going to print every element of it. Are there any questions about why it's doing that? It's just a new type. It's a little complicated, but hopefully it all makes sense. It is kind of pointing to that next element, and the pluses move it along. So I guess question 1, why? I guess your next question is probably, why should I care about this at all? It's so complicated. First answer is, secretly, that range-based for loop that you know and love, like saying for int x in v and doing stuff. Secretly, that's doing this. This code gets translated by the compiler into this code. So the iterators have to exist in order for this code to work. That's the first cool thing. So really, when you do a range-based for loop, the easy way, it's using iterators. And so you need to learn about those so that you can understand the quirks of it. All right. Second idea is every other container type. My second answer for why you should care. Every other container type in C++ also uses iterators, and they work in weird ways, but the interaction is the same. It's always ++, star. It makes it very nice. Okay? But yeah, here's how I want you to think of iterators to vectors, at least. So I believe that in any sane implementation of a vector iterator anyway, it's going to be using pointers deep down. Here's how you do it. So here's v. It's got 8, 6, 7, 5. Here's it. It starts out pointing to the 0th element of v. So that's the 8. And so you can think of it as like holding the address of the start of that vector. Like here's address 100. If these are ints, the next int is 4 bytes later. 108, 112. And then over here is 116. This is kind of how the iterator is working. At the start, it's pointing to address 100. You say star, it gives you the 8, ++ advances it. You print out the 6, so like here we are printing our stuff. Star it, it++, star it, it++, star it, it++. And then after this IT++, this is v.end. It's essentially the address of one past the end of the vector. You don't want to go there, so stop before you get there. All right, that's kind of how vector iterators are working. They're likely really using pointers, even though they've overloaded those operators, pointer operators. Okay, any questions about this? Vectors, iterators, yes? That's correct. And that also works even with pointers, even with pointer arithmetic in C++. If I had an int array, I don't know, and I had a pointer to the beginning of the array, like int star p equals r, right? That's a pointer to the beginning of the array. If I say int star q equals p plus 1, that will point to the 2 element even though it's 4 bytes away. C++ is nice to us. It calculates like how far should I really move. I just want the one next int, for example. Yeah, that's how it's working. Great question. Does that make enough sense? Good. Great question. Any other questions? All right. So yeah, that's vectors and their iterators. You're pretty comfortable with vectors, I'm sure. But yeah, let's move on to lists. So again, why would you ever want to use these iterators? Probably the main reason is they work in the exact same way for completely different container types. So a linked list, remember, a list, there's a list type in C++ and it kind of wraps around the idea of a linked list. So like here is the linked list container, the list container holding 8675 again. It looks completely different. There's a bunch of pointers moving around. Remember that from your book? And then there's like a null pointer at the end. It's very weird. C++ has a list type. It looks like it works just like this. You can push front, push back, pop front, pop back. It's a little fancier than vectors in some ways, but they also have iterators, begin and end. They're called the same thing. They work in the exact same way. That's wonderful. They work in the same way for completely different containers. There's no concept of .at in a list. There's no concept of indices in a list. But still, iterators will get you through it. Okay? So lists are an abstract data type. Really, you don't have to implement it like this. You could secretly implement a list with like an array or a vector if you really wanted to. It's just an ADT. It's a black box. It responds to commands like push back, pop back. It also works with the front too, push front, pop front, so add something to the beginning, which is very easy to do with a list. Ask for the size, stuff like that. Insertion and deletion to the back or the front in lists are constant time. That is not true of vectors. Vectors take a long time to add or remove stuff to the front because you got to shift everybody over. If you want to add something to the beginning of a list, like 0, you can just put it right there. Some pointer stuff. Very fast. So it's constant time. There are trade-offs going on. It is faster to do some things for lists, to use a list rather than a vector. So if you're just adding to the end of something or the beginning, there's no difference. You could have used a list as well. But yeah, they do some things faster than vectors, and they do some things that vectors can't even do. I forget if vectors even have a push front and pop front. Do they? Yeah, vectors don't even have push front and pop front. You'd have to do some weird stuff with pushing back and then shifting everything and then putting the new thing at index 0. It would just be a bad time. No. Lists, on the other hand, they just have push front and pop front immediately. Insert and delete from the beginning, at the beginning. So let me show you lists. It looks very similar to vectors. C++ is very nice to us. Let's see. So instead of including vector, I'll include list. That's where this lives. That's where this type lives. It lives in the list library. List. And here's how you can do it. I can say list int. It's a list of int, call it L. Instead of a vector int, call it V. So let's make a list holding 1, 2, 3, 4 in that order. Right now it's empty. L dot, but I'll do it in a weird way. L dot pushback, let's do 3. Pushback 4. And then I need to get the 1 and 2 in front of that, so I'll push front. Push front 2, so now it goes 2, 3, 4. And now push front 1. Now it's 1, 2, 3, 4. Can you see that in your head? So this is the list holding 1, 2, 3, 4 in order, and I can go through it. I can iterate through that list with a list iterator. Why not? So again, it works exactly the same. Even though there's no .at for lists, it will go through this exactly the way we think it should. 1. Let me draw this slightly better. So it's these nodes, right? Those are their technical terms for them. These are linked list nodes. 3, 4, kind of looks like this. That's the list that we just built up. I can use iterators. Start the iterator at the begin, right? Star IT right now would give me back 1, and I can say IT++ to advance it. Go to the next place. IT++, go to the next place. Go to the next place. And then the last place you can go is like nowhere, like nothing. The null pointer stops the list. Remember that? And so maybe that's the definition of L.end. Maybe their end for a list is just the null pointer. I'm not sure. But that would make sense to me. So let's implement this. Let's show that working. So for, instead of a vector of int iterator, it's a list of int : iterator it equals L.begin. It, keep going until you're at the end. Don't stop at the end. That's one past the real end. IT++. Cout, star it, exact same code, just with lists instead. Cout end L. And I have just traversed through a completely different container with the same style syntax. That is beautiful. Oops, sorry, not list.cpp, lists. 1, 2, 3, 4. Any questions about that one? Does that make enough sense? All the same, yet slightly different. Technically, if you'd like to go in reverse order, you can use it --. Like you can move around in a weird way. You have to like minus the end so that you start at the last element, though. If you really want to go in reverse through a list or a vector through iterators, there are reverse iterators rather than forward iterators. Okay, so there's instead of begin and end, you can use rbegin and rend. So rbegin is the last thing. Rend is like one before the first thing. You can do it in that way if you'd like. But yeah, this is exactly the same, remember. This is all what the range-based for loop is getting translated into. So I just as easily as I can traverse a vector with this kind of syntax for int I and L, I can do it with the list as well. Cout I space. Because this code is getting translated into this iterator-based code. So they're both going to print the list. All right? That is lists. Very similar to vectors, right? Okay. Next question, or next idea. This is a weird looking type called set. I can't even draw it for you very well. So what a set does, it comes from the set library, it stores a bunch of t's uniquely, there are no duplicates, and it also stores them in order. So for example, if I say insert 2, 1, 3, and 0 into a set called S or something, S is really just a cloud. It's a cloud of things, and it's being kept in order. So like, I insert a 2, okay, I'm putting it in me somewhere. Insert a 3, oh, that comes after the 2. Insert, it was the 1 next. Comes before the 2. Insert the 3, oh, it comes after this 2. Insert the 0, okay, that's first now, that comes before the 1. So it's keeping track of order for you. You'll have to learn about the fancy data structure that does this in CSCI 41, but that's what a set can do. A set works like this. It remembers ordering. It looks like my internet is slow. But you can insert stuff into a set, erase stuff, check the size, of course, check if it's empty. And what do you know? You can iterate through it. Wow. And all these operations, like insert something into a set, there's no like concept of push front or push back. It's just push in sorted order. That's why they call it insert instead. But yeah, it works like this. Just say insert whatever you want. Make a set of things. And its complexity is logarithmic in the size, which is probably as good as you can do with sortedness. There's kind of like a binary search going on. That's why it's logarithmic. So if you're trying to add something, add a new element into set S, if it's size 4, that addition of that new element, like if you add the number 42 to S right now, it would take log base 2 of this current size, so 4, log base 2 of 4 basic operations to get there, to add it correctly in sorted order. Okay. So sets know the order of their elements, and you get them out in order if you iterate through them in order. So let me show you that. This will be fun. So instead of vector or list, it's set. The library is called set. I'll make a set of ints. You can make a set of anything that's sortable. So let's insert 2130 like my example. S.insert 2, 1, 3, 0. And if I get them out, they'll be in sorted order. But you can also ask for things like S. You can check if something's in a set with the count function. It'll only ever be 1 or 0. Like count how many things are in this set with the value 2. It will only ever be 1 or 0, and you can kind of treat that as like a Boolean value. Count all the 2's, count all the 1's, and then like count all the 42's. So the answer should be 110, because a set can't hold duplicates. No, sorry, not lists. So yes, there is 1, 2. There is 1, 1. There are 0 42's. That's how you can check if something's there. And that's one thing a set is good for, just keeping stuff and knowing if it's there or not. But you can also go through it in sorted order. Get everything back out in sorted order. So for set of int iterator it equals s.begin. So that was the name, right? There it was. S.begin. It is unequal to s.end. However that's implemented. Who knows? IT++. We don't have to care. See how star IT, it all looks the same to us. Oops. And we get them not in the order that we put them in, but in sorted order. Yay. Oh, wait a second. What have I done wrong? 2, 1, 3, 0. Okay, yeah. I thought it was 1, 2, 3, 4. Saw the 42 and got scared. No, yeah. It's 0, 1, 2, 3. That's sets. Any questions about sets? Just another container. All right, last one. The final option, or the last one I want to show you today, is called map. A map is very similar to a set in that there is a sense of ordering going on, but a map can hold pairs of things. It holds pairs of things. It's like a lookup table. So there's 2 types in a map. There's the keys value. That's the type that you're using to look up stuff with, and then the value type. That's the thing that you get when you look up a key. All right. So a very common example of a map would be like a phone book. A phone book takes strings, like people's names, to ints, their phone numbers. So you store pairs of those things. So like if you make a map M, it's another cloud, and you can insert like pairs of things, like Lawton maps to my phone number, 555-1234, or whatever. All right? You can store as many things as you want, like maybe my cat has a phone. 1, 2, 3, 5. But it's always pairs. This is the key, and this is the value. You can ask the map, hey, what is Lawton's phone number? Hey, what is Lonzo's phone number? And it will give you back the corresponding value. Okay? That's the idea. And they're also based on, they're ordered based on their keys. Key and value, those are maybe new terms. And so you'd say map from strings to ints. Strings are the things you can look up. Ints are the things that you get back when you look them up. So yeah, it holds pairs of things, there's a mapping going on. That's why they call it that. So you can, of course, insert things. You can iterate through. The dot at is you give it a key, it gives you back the value. So this is a map of strings to ints. You can ask for or set at a certain place. Okay, that's the idea. So it makes the most sense with an example, as usual. Let's do maps.cpp now. Oops. Again, lives in the map library. And I like to use strings, so let's include the string library too. Let's make a phone book. That's a map from strings. The keys are strings. That's what you use to look up people in the phone book, right? And then ints. Boop. And now I can add stuff. There is an insert, but the cool kids like to use something called inplace instead. So phone book.inplace. And here's the key, like Lawton, and here's the value. All right, so this is me adding this mapping into the map. Please, whenever somebody asks for the key Lawton, give back the value, this number. Okay? And so those are the two things in my phone book. You can check if somebody's in the phone book with the count function again, count method. Phonebook.count, again, it'll only ever be 1 or 0, and you give it the key that you're looking for. Hey, is Lawton listed in the phone book? Hey, is my mom listed in the phone book? And it's not. Oops, sorry. Can't talk and type. The count gives you that idea. Maps. So yes, I am in the phone book, but my mom's number is not. And then you can go and look. You can say cout. Well, I guess you can ask for .at now. .at. .at. It will not work if it's not there, though. I'll throw an exception. But the first one will work. So that's why you should always check, hey, is it there first? So here's this line, phonebook at Lawton. That just goes into the phone book, and it finds the value associated with the key Lawton. There it is. And it gives you back that number. It's very quick about doing that. All right, but this one will throw an exception because it's not there. And then again, you can map through a map, or iterate through a map with an iterator. Let's see. Anything else do I want to say before I do that? Okay, yeah, maps, because they have a concept of ordering on the keys values, they're just about as fast as sets. Instead of storing just one thing, you store that pair of things. Logarithmic time to add stuff, retrieve stuff. And iterating through looks like this. For map string, you always have to give the original type, right? It's a map from strings to ints called phone book. Right? So map string int iterator it equals phonebook.begin. It is not equal to phonebook.end. It plus plus. It's all the same, but when you iterate through a map, because you have those pairs, you have strings and ints, it does not, you can't just say star it anymore. You have to dereference it, and that gives you a pair of things that has a first and a second. So here's how it works. Cout, it's it's like an object that holds two things. It's a pair, a first and a second thing. So I can dereference and use the dot on it with the arrow operator and get the first thing, that's the keys value, and then it second would be the values value. So my name, my number, my cat's name, my cat's number. Go through them all like this. And I'll draw a little arrow to indicate the mapping. So this is me going through that map, getting everybody. I guess my name comes before Alonzo in the phone book, or in the dictionary, so that's why I would give it in this order. It's sorted by keys, and so it's keys and values. So here's me printing the key, here's me printing the corresponding value. Here's me printing the key, printing the corresponding value. And here's me accessing the phone book at a certain key. It gives you back the corresponding value that's stored there. Okay, so maps are good for like a lookup, looking up from one type to another. Any questions about any of that? All right, so now you've seen them all. Can you keep them all straight in your head? I have a question for us. You can get into groups if you'd like, but let's go to the buy clicker page, please. I have some just rapid fire questions for us. So here's my first question. Let's do number 1 first. So pick from A, B, C, and D vector list set map which container would be the best to hold a bunch of Pokemon cards and their selling prices. Because that's what millennials like to do these days, buy very, very old Pokemon cards. There is no right answer, but I want to see what you think. Discuss as a group if you'd like to, but take a few seconds, get in, discuss, and get in your best guess for what the answer should be. There is not just one right answer. There's plenty of right answers. Pick which one you think is right. Should I put them in a vector, a list, a set, or a map? We're doing number 1 right now. Think about the operations involved, how you'd want to add them. Which things are faster than other things? Which things are impossible with certain data types? All right, take a few more seconds to get in your answers, your ideas, and we'll go on to the next one after we discuss this one. All right, let's take a look at what we're thinking. Ooh, look at us. B, C, D, none of us think vector. Interesting. A couple of us think lists or sets, and a lot of us think maps. Why maps? Why is that a good idea? Nice. You could associate, the card with its value. It could be like a little phone book kind of thing where the key is the name of the Pokemon and the value is its current price. That's a great idea. I think any of them are valid options, though. It really depends on what you want to do with them. You can make a Pokemon struct type, struct Pokemon, blah blah blah. You can hold the key and you can hold the name and the type in that struct, and then you can make a vector of those structs, a list of those structs, a set of those structs. That would also work. It just depends on what you want to do. If you want to look up name to price or something like that, then it's a great idea to use a map. Otherwise, if you just want to like have them so that you can display them or print them out, anybody else would also work. Does that make sense? There's a trade-off. It depends on what you want to do. Okay. That's the idea. All right. Question 2. Let's try this one. So please take a few seconds to discuss. How would you hold? What would be the best container that would hold like a group of people waiting in line, or I don't know, a group of virtual people trying to buy Taylor Swift tickets? How would you store that? What would be the best one? A few more seconds. maybe start thinking about the other ones in your mind while we got these going. Yeah, I'll give you like 15 more seconds to get an answer in for this one. And again, there's no one right answer. All right, 5 more seconds. 5, 4, 3, 2, 1. All right, let's see what we're thinking. Ooh, all right. I'm not so sure. It looks like list is winning, vector list. Maybe set. No real concept of keys and values, so maybe a map isn't a great idea. Again, I think they would all work, but we're really thinking lists. Why lists? Why are lists a great idea? I agree. Lists are a good idea here. How so? I think the idea should always be like people are going to come to the end of the line. So vectors and lists are great ideas because you can always add to the end, right? That's the new person about to wait in line. It really depends on what you want to do to like pick and choose whether a vector or a list is better, though. Maybe you would like to like, I don't know if Disneyland even does this anymore, but like fast passes, remember that? People can cut in line. If you'd like to add them to the front, you really need the push front on lists. That doesn't exist on vectors. That might be a great idea. And also, if like this is it's a bunch of people that are eventually going to be served, like the people at the front will be served, you want to get them out, you need to be able to pop front. And that's the only one, list is the only one that can do that, right? You want to be able to pop front. But if they're all just going to stay there in some order, vector works just fine. Set, I can see how that wouldn't be a great option, right? Because like there is a concept of ordering, but maybe it's not the ordering of people in the line. But maybe you could store in your number, like in your struct, you can store it in a way such that it's compared to give some kind of priority level. So set could also work. So that would also be a good idea because you could order by like the priority of people in your line. And technically, I guess you could also use map. You can just like have ints as keys, and like key 0 could map to the first person in the line, key 1 could map to the second person in the line, etc. It would be a little complicated. Again, they all work. I think I would choose list 2 though. Nice. All right. Let's do the rest kind of quickly so that we can talk about other programming languages. Let's do number 3. I'll give you like 30 seconds to get something in for that one. So a bunch of students on a class roster, like I don't know, it depends on what you want to do with that class roster, but how would you store that container, that amount of students? Maybe you'd store their names and their student IDs, etc., etc. Make a struct of them. Would be the best thing to put it in there. Put a bunch of students in. All right, a couple more seconds. And again, there's no one right answer. I'll give you till a minute. All right. Yeah, we're not sure, and I mean that's totally fine. Let's see, A, B, C. So we're thinking set. A lot of us are thinking set. I could see that if it's ordered by something. What would it be ordered by? How would you order your students? Maybe by last name, student ID. If you're trying to like submit grades, you could order by grades or something. I think a set would be a good idea, yeah, because you could start changing the way that you order things. But I mean, I think a vector would also be a good choice. Maybe because like you can start it in sorted order by their last name, and you can sort it in any other order. Like maybe you've used like filters in Excel before. Like you can sort by different things by giving a different kind of sort to the sorting function. You can give a different sorting or comparison idea to the sorting function in the algorithm library. And so a vector would also work. Again, it depends on what you're doing with them. If you're like just checking off, hey, is everybody here? Like you can just call everybody's name and pop them off the front if you're using a list. Maybe a list would be a good idea for attendance or something. And yeah, a map also works. Like you could map students' names to their IDs. It all depends on what you're trying to do with the data. I hope that makes enough sense. Okay. So yeah, let's do the last one just real quick, and then we'll talk about it. So if you'd like to store the last 100 days of Bitcoin prices and cry about it, probably, what would you use? Take another 15 seconds or so. All right. E. Yay. So, all right, we're thinking vector, and yeah, I can see that. Is anybody really confident uh, in their choice? Would like to explain their answer? Yeah. I could totally see a mapping here. Like you could encode the day with you could encode the day as maybe a string. Like you could encode November 13th, and you could be able to look that up immediately. That would be a great way to do it. Yeah. So map, I could see. We all like vectors. You could store it in order from like 100 days ago, 99 days ago, 80, 98 days ago. You can keep it in that order. That would work. It just all depends on what you're trying to do with it. If you're trying to look up the price on a certain day, a map is probably a great idea. If you're trying to order by like how expensive was it, how cheap was it, maybe a set's a good idea. Stuff like that. If you just want it to be able to look at it and iterate through it, a vector or a list equal would be fine. Okay. Any questions about any of that? There are a bunch of trade-offs. It all depends on what you want to do. Which container you should use. Does that make sense? All right. Good discussion. Very good ideas. In the remaining time today, I would like to do a fun thing. I promise to not test you on any of these slides, this set of slides, but for your knowledge, I would like to teach you some things other than C++. If you go, depends on where you go to a four-year college. A lot of the students there will start with, some schools, they do teach C++ as their first programming language. That's why we're teaching it to you first. But other schools, they start with Python. Other schools, they start with Java, among other things. And those are the two most common. So those are the ones that I'm going to show you little previews of today. And if you're interested, I can help you find more information about them. So I promise not to test you on non-C++ on the final. This is just for your knowledge, all right? To help you when you transfer to a four-year college. So yeah, let's talk about Java first. This used to be like the traditional language that everybody would teach, but it's a bit less popular these days, I would say. But very, very popular still in industry. So if you'd like, there's a cute little website called Learn X and Y Minutes, and X can be Java. Let's close this. They have a nice little documentation page that just has a really long text file and with a bunch of comments, and it walks you through some features of Java. It's a great place to look if you just want to like brush up on the language and get a feel for it. All this syntax, it looks a lot like C++, surprisingly. Some weird words, import instead of include, a bunch of system.out.println, that's their cout, essentially. Doubles, floats, ints, those all look the same, semicolons, those are still there. Instead of bool, they spell it out, boolean. So go ahead and look through this page if you'd like. I'll give you some highlights though, all right? Oops, not that one, this one. So yeah, it's surprisingly similar to C++. They're both trying to cover the same ideas, and so they look the same. it's another object-oriented language, so it's built around classes, the idea of classes and methods. And once you learn one of those, you essentially know them all. So Java will look very familiar to you. Python might look a little weird, but all the concepts will still be the same, essentially. Okay, so here, let's do the quintessential example when you learn a new programming language. You have to do hello world. You have to make a simple program that just prints to the screen so that you can make sure you understand what's going on. All right? So let me show you hello world. Boop. So I'm gonna, for the very first time in this class, say vim hello world.java. That's their extension. It's .java. And they really like their camel case, so it's capital H for hello, capital W for world. You can spell it however you want, but this is their standard way of doing things. Capital names for classes. Camel case everywhere. All right, so here's the file. Let me just start typing and then I'll explain it with comments. Public class hello world, parentheses. I don't need a semicolon at the end of class declarations, which is beautiful. Everything goes into class, though. Public static void main, string with a capital S, bracket, bracket, args. That's your command line arguments. You're forced to ask to have them everywhere all the time. And then system.out.println hello, comma, world, exclamation point. The new line is included in this print. It's print with a new line, println. Print an entire line just like this. So this is hello world in Java, and let me explain it because it looks a little weird. So, all right. In Java, first of all, everything is a class in Java. They really went hard on object-oriented programming. You can get away with just functions in C++. Cannot do that in Java. Everything is a class. So that means everything is a method as well, essentially. In Java, everything is a class. If you just want a function, and we just want a main function, essentially, you need to put it inside a class. And then you call it static. Static is kind of the idea of functionness, even inside of a class. It just belongs to the class itself, not any object. That's the idea. So we're putting all of our stuff inside of a hello world class. So hello world is public. You have to put the access modifier right next to everything. You can't just say public colon in Java. So it's visible to the outside world. Everybody outside of this file can look at it and import it instead of include. It's import. That means other people could import it and use it if they wanted to. Right? But we're just going to use it ourselves, compile and run it, just this file. And then, all right, that's public class hello world. When you use Java, if you have a public class, if you define a class, they really want you to separate your classes by files. If you define a public class that's visible to anybody inside of a file, and it's called hello world, the file that it's defined in must also be called hello world.java. So I am not allowed to call this public class anything else. I can't lowercase it. I can't do anything. Once I pick the file name, the public class has to be hello world. That's one weird thing Java does. Kind of keeps us honest. Makes it so that you can immediately find where a class is implemented, I guess. That's nice. And then here's the main function. So the main function lives inside the public class associated with the file. So this is hello world.java. So the main function would live inside the hello world class. You must use the definition below. You can't just like get rid of the args or anything, even if you don't want to use them. You have to always ask for them. You must use the definition below. Args are the command line arguments. There's no argc. This is just argv essentially. Command line arguments. String is capital S, and bracket bracket comes after the type to declare an array in Java. Right? These are command line arguments, even if you're not using them. Right? So in Java, args is an array of strings. And to declare an array, you put the brackets next to the type rather than the name of the variable. That's the difference. And main is a public method inside the Hello World class, so that's why we say public here. It's also a static method. Static exists in C++, and I encourage you to look it up. It means it belongs to the class. It's not an objects thing. It's Hello World's main. It's not like some objects method. It's also static. It's complicated to explain, which means that it, lots of comments today, it belongs to the class itself rather than to any object of the class. Please look up this idea if you're interested, if that's a little weird. Finally, there's no concept of separate declaration versus implementation. You don't have to declare any functions / methods in Java. You just go and implement them. It just finds them no matter what order everything's in. It's like you don't have to put one thing above another. Java can just find everything. It just finds them no matter what order you put them in. Okay? So that's the file. Lots of comments. Public class hello world though. Wrap around everything, and then the main function is public static void main. Doesn't return in, there's no return 0. It's just void. And here's the one line in the main function. Okay. So that is the start of it all. If you want to know why is that where you print stuff, let me try and prove to you system.out.println. There's a wonderful documentation feature of Java. They're really good on documentation, but they're also really bad on naming things. Here's a bunch of very long named things that are here. So system, the system class, lives inside of java.lang, java.lang package. And so that's where system lives. System. Oh, come on. Let me just try and scroll to it then. System. Inside of system, there's an object called out of type print stream. And every print stream has a method on it called println that could take a bunch of different things, one of which is a string. That's the one we gave it. There it is. It prints that string and then terminates the line. So very nice documentation for Java. That's all baked in. So that's why it's system.out.println. Java.lang is automatically imported for you, though. And all right, we've made our program. Let's compile and run it. To compile, you say javac. That's a Java compiler. Javac for Java compiler. So you say javac and then the name of the Java file. So javac hello world.java. Hello-world.java, hit enter, and it picks the name for you. It made a file called hello-world.class. That's the compiled form of it. Okay? That's the idea. So compiling hello-world.java makes hello-world.class, and then you have to run it. You can't run it with / because Java is not technically a real machine code compiled language. It's a bytecode compiled language. You have to run it in what's called the Java virtual machine, which is way too complicated for a first lecture on it, but I have to say the words at least. So Java, you have to run it with the Java command. Java hello world, it'll find the class file and hit enter, and we have a program. Yay. Hello world. Are there any questions about anything that I did? Is there anything overly complicated? So I have one last example for the day, and then we'll do the rest next time. Okay, and again, I cannot change the name of this. If I misspell it, hello world, try a javac, it is going to yell at me. Oh, sorry, that's public, but it should be declared in a file called hello world.java. Shame on you. There we go. So that's the idea. That's what's happening there. All right. Let's go back to some differences between Java. So pretty much everything is a class. There are no pointers in Java. There's only things that it calls references, which are different than what we think of as references in C++, which is unfortunate. And then arrays look a little different, like the brackets go next to the name and stuff like that. But a lot of the syntax is the same as C++. So let me give some examples of that. Let's call it more java.java, with capitals and camel case, of course. And then if this is what I called the file, if it's called more java.java, it needs to have a public class called exactly more java. Right? And then the main function will live here. It's public static void main, string args. And yeah, let's do some stuff. Ints look exactly the same. Int x equals 42, semicolon. Exactly the same as C++. Double y equals 3.14, exactly the same as C++. Instead of bool, it's boolean. You gotta spell it out. It's boolean value. Boolean b equals true. Still lowercase though. All works out. Strings are capital S though. String s equals hi mom. Double quotes and everything still. Arrays. This is where it gets interesting. Arrays, first of all, you say int bracket bracket r. Second of all, arrays must be made on the heap in Java. A lot of stuff needs to be made on the heap in Java. But there's no need to ever call delete, which maybe get into that today or tomorrow. I guess we can talk about it today. So arrays must be made on the heap, and the bracket bracket goes after the type instead of just the name. So int bracket bracket r equals new int bracket bracket, and then in braces you put what you want to put in the array. 1, 2, 3. I believe there's a way to make an array of an arbitrary size without actually giving values, and I think they're all defaulted to 0. If you do that, it might look something like this. I forget though. But this is how you give it values initially. And the third cool thing about arrays that we really would have liked to have in C++, remember how you have to, if you use arrays, right? You need your argc. You have to pass around the size of that array everywhere because it does not know its size. All arrays in Java know their size, which is lovely. And you can access it with the dot length, like it's essentially an object secretly. So in that case, if I'd like to iterate through this array, for loops still exist. For int I equals 0, I is less than r dot length, not size, just dot length, and it's just a member variable. It's not like a function. I plus plus system.out.println r of I. Okay, all the same, just slightly different. And then, so Java C, more Java. That compiles this into a file called helloworld.class, or sorry, more java.class, and I say Java, more Java, without the .class, it'll find it, and then it runs the program. So that prints my 1, 2, 3. Any questions about any of that? If you remember, let's see. I'll talk about all this in just a second. If you remember, when you say new in C++, you have to also say delete, otherwise you leak memory, right? You lose that thing on the pointer, it's gone forever, you have no way to get to it again. That's a memory leak, that's bad. Java takes a different approach. No delete is necessary in Java. It takes care of deletion for you, which is lovely. It figures out, like it's able to tell, it takes a little bit of extra work, so Java is slightly slower than C++, but it's still pretty fast. It notices when we're finished with something that was made on the heap, with heap memory, and deletes it for us. And that deletion process, that automatic deletion process, there's a cute name for it. It's called garbage collection. And it garbage collects it. So, yeah, technically, There are no memory leaks in Java. It's impossible. It will get rid of things for you once it notices you're done with them, which is quite nice. So yeah, that's the program. Let's talk about it a little bit. So first of all, Java is not run on the CPU. There's a step between the CPU and compiled Java code, which is different from C++. Java runs on what's called a virtual machine, right? So when you compile Java programs, you compile them into a form that can technically actually run on any computer that has Java installed. So that's different to C++, where when you compile it on my computer, it will be completely different than if I compile it on my Mac, which has an ARM processor. It's a different machine code. It would not run. Okay. If you compile it on Java, you can run it anywhere that the Java virtual machine is installed. So there's a little step between running, though, right? So let's talk about that. So more Java.java was the name of the file that we wrote. That was the text file. Public class, whatever. ... So that was the file. We compiled that to what's called Java bytecode, and that was the class file. This was more java.class. And that is a binary file, ones and zeros. 1, 0, 1, 0, 1, blah, blah, blah. It's not yet runnable on the CPU yet, but it's runnable in the Java virtual machine, we say. So this is called bytecode. It's not machine code. All right. In order to run this class file, you have to have Java installed. Also different from C++. If you compile a C++ program and just give it to somebody, they can // it. It's just fine. It's already machine code. You don't need the compiler on their machine. In Java, you need the Java virtual machine. So here's the black box that you got to give the class file to in order to run it. So Java virtual machine, or the JVM for short. And that's the thing that runs the code for you. Runs the code for you on the CPU. That does the final translation to actual machine code so that you can run it on your CPU, and it's pretty fast. It's slightly slower than C++ because there's this intermediate step, but it's still pretty fast. Let's see. Yeah, all arrays were on the heap. Pretty much everything in Java is on the heap because it's garbage collected. You just say new and it calls delete for you, which means that like you can put more things on the heap and just not worry about them. So that was their approach. So if you make some stuff on the heap, they will stick around as long as you need them and are using them. But once it notices like a potential memory leak, like I don't have access to this thing anymore, it can never be accessed by the program, well, then I'm going to reclaim that memory because obviously no one will ever use that thing again. That's the beauty of it. There's also no concept of like pointers, like you would have thought that this would give back a pointer to something, but now it gave back the array, or it gave back an object, it gives back a reference, but you don't use ampersand. It's just a little bit weird. I think we'll talk about that a little bit more next time. All right, but this is the program. It looks all the same for the most part. For loops are all there. The syntax is very familiar, I would say, and you run it like this, and it prints out the array. I think that's everything that I want to talk about today regarding Java. Are there any questions about it? We'll come back through some cooler stuff next time, then I'll also talk about Python. But let's see. Yeah, that's everything that I want to talk about today. We'll have one more lecture on that next week. We only get one lecture because of Thanksgiving. And then week 17 will just be final review. Okay, so that's my plan for us. We're almost to the end.